Okay, so we've got Adrian Smales on health, IoT, robotics, and digital evidence. Adrian has a PhD and is a part CIO, part cyber wizard, part data whisperer, and he's led transformations across all of Europe. And I'll hand over to you.
Thank you so much. So yes, thank you very much for my introduction. So I'm here for a good time, not a long time. So if you have questions, please do feel free to ask. This is a bit of a ramble, hopefully coherently threaded through a particular presentation that I am about to give. Okay? So if you have any questions, you can say them to the end, or you can kind of throw your hand up and we can kind of take it as we go. We may not get to the end of the presentation then, but you know, this is like 45 minutes you'll never get back. So it's much your life as it is mine, really. Okay? So yes, this is about health, IoT, robotics, and digital evidence. This is the same presentation that I gave to Interpol when they did the gathering in this lecture theatre a few months ago. Okay? So if you attended that, I do apologise, you're about to get it again. But it was a good presentation and well received. So hopefully you guys will like it. Okay, so as you can see there, we'll start off with an understanding of what our definitions are, right? Health devices, as you can see, we're speaking really about connectivity, okay? So health devices that in some way reach out to the real world to provide your data to somebody else for a variety of reasons, okay? So wireless programmable implantable medical devices, we call those IMDs, such as pacemakers, implantable cardiovascular defibrillators, so these are very invasive devices that perform very important functions within the human body. Without those devices, or if they malfunction, you will probably cease to be. So it's very important that they don't get hacked at all, and they don't malfunction, okay? So these devices perform a core group of really life-enabling and life-preserving devices. It's very important that we understand how they behave and prevent them from being hacked, okay? But we do a particularly bad job at that. For various reasons, mostly commercial and ease of use, right? Security is the last thing that these guys are thinking of. So it's a problem. It's a problem. So what else? So all pacemaker programming and interrogation before 2026 was performed using inductive telemetry. Do we all know what inductive telemetry is? You had to be physically present, and there was a coupling device, usually using some kind of induction between the implantable device and a sensor that would be placed on top of your skin. Okay? So that there would be a direct magnetic coupling between the sensor and the programmer. It wasn't a radio wave necessarily that transmitted over great distances. Okay? So it was relatively secure. You would have to, for that to be hacked, you would have to be sedated or sat next to somebody who you knew had some device in very close proximity, usually on your chest, while they tried over several minutes to reprogram or hack the device. It would be pretty noticeable for you, right? So those would be very useful. So we say very close skin contact, near field. So this is kind of what your RFID is, okay? But instead of RFID just transmitting one thing, this is a two-way communication, right? So near field, sub 1 megahertz, data rates very slow, less than 50 kilobytes a second, right? So very secure, actually, in what it would do, but not particularly practical if you want to make changes on the fly, right? So this is one of the things that I want to get into because has anybody seen Homeland? Those who have, put your hand up. Great series. If you haven't seen it, I recommend you go find it. Okay, very good. So there was a particular episode and they kind of hypothesized within Homeland that you could hack somebody's pacemaker. And how plausible is that? And this particular article was almost like an expose on going through that particular storyline and then trying, you know, because this is a popular series, people might not know, and it was used within, you know, a populist kind of program. And how plausible is that? It's not just plausible, it's actually very, very doable. And that's one of the challenges. You know, this is the smoking gun. And I believe it was one of the, either the, not the vice presidents, but one of the American kind of heads of, that was in charge of security at the time. I'm thinking it was Donald Rumsfeld. I don't think it was him, but it was somebody like that, who actually did have a pacemaker, and they had to disable all wireless communication to it. Because it would be so easy for a nation state to be able to infiltrate whatever was necessary. Hi, Basil, grab a seat. And shut it down. And so we'll go through some of the stuff within this to demonstrate how that is possible through people researching this. So, hacked devices found vulnerable to attackers. Okay, so you can actually see there, right? The long list. So this is where the New York Times picked up that, and they found it to be highly plausible, right? So this is now moving from just a theory in a TV series to journalists doing some very serious research into understanding the nature and the issues around these kind of implantable devices. This is the proceedings from the 20... So as we're moving through the timeline, right, this is in 2008, a couple of years from that, and pacemakers, implantable cardiac defibrillators, software radio attacks, and zero-power defenses. The column that you should be interested in is the third column on the right, because the bottom three ticks, right, are pretty much where they kill you. I mean, you can see from there, look, change the device settings, change or disable therapies, deliver command shock. That last one would stop your heart. And you can do that. It was found that you could do that. Right? That's pretty much where I can remote control your life. You live, you don't live. Okay? So it's pretty serious stuff, right? This is not something that is trivial. This is something that is absolutely life critical. Okay? And the device that gives you life, when the surgeon implants it and says, "You're all good now, Mrs. Smith or Mr. Jones," some hacker, if you have a particular role or a particular job that makes you either important or vulnerable to suggestion or control, this is one way that you can exert that pressure. Right? At any time, for any reason. Okay? Not good. Not good at all. Not good at all. So, to remedy the distance and speed limitations, manufacturers began implementing radio frequency RF communications. So one of the challenges, and this is the tension between the industry and security, is that they decided that this security and this low data rate was a problem to their devices being much more accessible. So they want them to be able to be changed on the fly and monitored more frequently. Because why wouldn't you, right? If security is not your thing, you would want your devices much more accessible, much more usable, much more friendly in terms of the data that they provide you. So they do that, and then they up the frequency. So interrogation programming from greater distances, faster data rates, and in 2006, the FDA began approving fully wireless 5G pacemakers and ICDs. 5G, if you're not familiar with it, is mobile data. I can touch you from anywhere in the world at that point, right? So distance is no longer a problem. You being next to mobile data is the only defense that you have. So if you're in Cornwall somewhere, it's difficult to get a mobile signal. It's terrible. So lots of people with pacemakers like this should live in Cornwall, because no one is going to be able to get to you, because it's particularly shit down there. I know Wi-Fi is terrible, right? So, you know, squirreling yourself away, hiding under a rock, if you've got mobile signal, they can get to you. If you haven't, you're okay. So this is one of the manufacturers, right? Hacking risk leads to recall of 500,000 pacemakers due to patient death fears, right? That's 500,000 people who went under the knife to have one of these pacemakers. It's not going to, it's not like Ford ringing up and going, we need to replace your airbag, right? This is a bit more serious than that. This is the thing that keeps you alive, right? And then somebody phones you up and goes, yeah, we have to have a recall because you need to have a major operation again where we replace your pacemaker because actually it can be hacked and you can be killed. That's not a good thing to have, from your cardiologist over the phone because the manufacturer decided, security is not our thing, but convenience is. Yeah, conveniently, how conveniently I can kill you. So this is it's a big problem. This is a big problem. This woman, unfortunately, suffered cardiac incidents and was given a pacemaker. She also happens to be a very competent cybersecurity expert and decided, because she couldn't get any answers from the people that manufactured her pacemaker, how hackable is my pacemaker? It's in my own interests. I actually understand this stuff at a fundamental level, right? And they wouldn't give her any answers because it probably wasn't great. And it would open them to lots of liability if they admitted, yes, we implanted a non-secure device within your chest to keep you alive. You can imagine the lawsuit that would ensue after that, right? So she decided to hack her own pacemaker. And she did. And she found out that it was very, very vulnerable. Okay? So much kudos to her. So then we go on to this low-loss MIMO antenna wireless stuff. So the manufacturers, notwithstanding all of the stuff that's coming from the industry about how these devices can be circumvented, how insecure they are, that long-range communication is not really a good strategy for security, these guys go and double down on that and go, actually, we can make it even better because wireless technology improving so much, we'll create low-loss MIMO antenna wireless communication systems for 5G. Not only do we want to make it more secure, we can do that at even greater complexities now with MIMO antennas based in your chest for even greater fidelity of that communication. And so these guys are really doubling down because why not? That's what researchers do, right? They find how to do things with greater efficiency and greater speed. And unfortunately, the reality of this is that the practicality of killing somebody was not even considered because their job is to look at the communication between the device, right, and the outside world. And how can I create greater range? How can I create greater fidelity with the data that I'm sending? How can I reduce, how can I connect to that device with greater certainty? Not greater security, but greater certainty. Because the security is not about the communication. It is, but not just. It's the how hard is the device. Did we do anything on the device to prevent and secure it? Probably not. Right? And so this stuff is fantastic. This is if you're a comms engineer, this stuff is phenomenal. If you're the guy on the table having it implanted into you, not so much. Right? Yes, the cardiologist will go, yeah, don't worry about it. When you're at the gym, you're having a hard time, phone me up and we can do a few tweaks, give you some extra, beats a second or whatever, and, carry on. Yeah. So, the implications of this. So, we're now moving into a world where we try and understand this more and setting new standards for wireless medical devices. So the FDA are becoming aware of this challenge and this major tension between connectivity and security for these medical devices, right? Because there have been recalls, there's been a lot of noise now in the industry about this kind of stuff, and it's not all good. So, we now have the US government paying a lot more attention, right, around this. And the FDA particularly, right, the US federal government is increasingly more focused on regulating cybersecurity of medical devices, which is a good thing, because it then puts the onus of these medical devices and security right back where it should be, at the manufacturer. Because if you can't get them FDA approved, there is no way that you can get them implanted. And that's just in America, but they drive so much of that medical field globally. This is very important. We actually, in the UK, regulate our own devices. FDA is not an approval that we recognise in the UK. They have to be UK CA authorised separately to FDA approval. And also European standards as well apply for some stuff into the UK. So a new mandate by the Food and Drug Administration, the FDA, was effective, and this is very recent. I mean, this is 2023, right? October 2023. The FDA will refuse to accept medical devices associated with systems with cybersecurity concerns. Not flaws. They just have to have a whiff of a concern now. And they'll be going, no, we're not accepting that, right? Because there is too much ambiguity about what concerns are. And as we project this into the future, there are also zero-day attacks. There are all very many different facets that you can use against these devices. So if we have any concerns at all, we are going to fail safe now. And we are just simply not going to accept it. It's for you to demonstrate that there are no issues with your device. And if there are, forget it. Which is great. So what happens next? So the requirements, this is the section of the FDA Cosmetics Act. Note that medical devices manufacturers take their products to market, they must. So these are the criterion over which we need to make sure that they are secure. Monitor and address cybersecurity vulnerabilities and exploits, right? Including coordinated vulnerability disclosure and related procedures. Have process and procedures to provide a reasonable assurance. What they mean by reasonable is not, well, we tried. No, it's you exhaustively tried, right? You exhaustively tried. So this is about using state-of-the-art processes and procedures to try and prevent. Not we gave it a go, we gave it to an engineer, he had a play and, you know, we tried and it's documented. No, we exhaustively tried. So the standards are significantly higher. Provide software bill of materials, including commercial, open source, because a lot of this stuff is written with students, potentially off-the-shelf packages. We have examples where, you know, various different cybersecurity components have been written by PhD students in the past, put into a particular package, then rolled out into industry, later to find it was a whole crock of shit, right? And nobody checked. It's open source, right? Who cares? You know, so these are the standards that come out. Defines the context of cybersecurity assurances and wireless diabetes devices, and also specifies security requirements and provide instructions on how to achieve that assurance. So not just so the fit and the form, right? How we do it and what is the result and how do we check that? So this helps manufacturers provide instructions to them to be able to implement these new standards within their medical devices, okay? And they also have to make sure that they adhere to those standards as well. So these are now coming in, and all of these standards will be coherent across a lot of the hardware that's coming out. So these focus on one or two at the moment, but actually they will be rolled across the whole plethora of these kind of IoT devices. So, it's a problem. Even the latest health cybersecurity standards have not identified the need for critical devices to contribute to digital evidence, okay? So, we've never mentioned logging at all. We've just mentioned the cybersecurity. These are eyewitnesses. You drive your car, you have your pacemaker. These are all eyewitnesses to any event, right, that could prevent you from achieving that goal. It's a problem. So, ensuring non-repudiation in device logs for autonomous systems and medical devices. If you implement device logs, memory is cheap now. A gig of memory in this that would roll over, right, every 24 hours or every 48 hours or every month or whatever. So you have a history of what happened. That is the eyewitness. If anything happens to you, can be, it's the black box recorder, right? Planes have it. We've known in mission critical systems where these are absolutely necessary. Where's the black box recorder in your Tesla? There isn't one. There absolutely should be, okay? So, objective, designs technology for non-repudiation in device logs, health devices, IoT, autonomous humanoid robotics, and autonomous cars, to enable digital evidence collection for investigating major failures. And that's what we're talking about. We're not talking about minor stuff. We're talking about life-threatening devices and the major failures that will occur. It's inevitable. So, non-improving technology, what can we use? All of these you'll probably know. Immutable logs, timestamping, digital signatures, hashing. All these are available in very small footprints now, to varying degrees of security. These are not difficult to implement for manufacturing at that stage. So health devices, detailed activity logging, sensor data logs, decision logs, interaction records, and audit trails. These are the things that actually determine what was it trying to do at the time of failure. Who was talking to it? What was it talking about? What environment was it in? So you can then replay these, right, and understand the nature. And that's what they do with a black box recorder from a plane. So, immutable logs, use blockchain, timestamping. We need a time base. We can do this. Digital signatures, so hashing, all this kind of stuff. So these are the technologies that we can use for that. Sensor data logs, record raw data from medical sensors, decision logs, interaction recordings, and audit trails. So again, these are not difficult to record, and the data that they would consume, or the amount of storage they would consume, is minimal in today's standards. So for IoT devices, we need sensor data, service interactions, okay, network activity, and some kind of environmental context in most cases. So this is really understanding the nature of the device in all cases, and recording the stuff that makes that device unique to that person or to that environment. So when we're looking at humanoid robotics, and you'll come and hopefully find me later on, I've got Spot down there. It's not humanoid, it's a quadrupeded technology platform, really. But it can be controlled autonomously. It can do its own thing, right? If we program it to do that, it absolutely can. So you need fusion sensor data, decision algorithms. What was it considering? What was it processing? What was its real interest in being able to complete its task, right? Control commands and human interaction responses, HRI. Autonomous cars, right? So, as we've seen, Tesla is not immune to having a crash. The decision processing that it does, while potentially relatively good, it's not perfect. Any sensors that are not performing as they should be can cause sensor overload, sensor errors, and that will then affect the decision making that it has. That's imperative to be able to know that. Okay? So, implementation considerations, right? So from a manufacturer standpoint, we're talking about efficiency. Anything that we do to these very small devices will impact the performance of it. So you don't want your heart monitor to stop working because it's trying to process its logs, okay? So it will take a little bit more power. But we are in a world now where actually we have abundance of processing capability for very, very little power. Logging is not the issue. It's the appetite to be able to do it that's the issue, not the technology. So data retention, right? How do we offload that? Accessing and analyzing the logs. So these we need new tools, we need new systems for doing this. Tamper detection and prevention, okay? So these are the mechanisms for that. We do that all the time. And compliance standards. So these are the standards that we need to make sure that we adhere to. Healthcare standards, IoT standards for GDPR, for example, robotics and vehicle standards. And so we really need a comprehensive review to be able to do this. So this is an industry-wide challenge. And we need standards to be able to make sure that we can have all of these solutions and standards in place moving forward to make sure that we have very and highly secure and defensible devices, especially if we're going to get into humanoid robotics that are going to live and work alongside us. Okay? Because that actually is the future. So, thank you very much. Any questions? Yep.
Sorry, outlined the legal pressure on companies that kind of enacted the change. How do you view the recent massive cuts to the FDA and the Justice Department that are enforcing those things by the Trump administration? How do you view that in the future?
So, my own political biases aside, because I think it's a complete travesty, this is, at this particular time in history, when we need something like this the most, history will not be kind to these people. Where we are now pioneering. So we are, Bill said, we heard what Bill basically said, in his presentation. Most of which I agreed with, the detail of which is not quite right. I can have a chat with Bill about that. But LLMs, what he means by LLMs are agentic LLMs. LLMs by themselves are terrible at doing anything to do with number crunching. They are. What an LLM will do is literally statistically tell you what the next token is within the sentence based upon my input to it. That's what it's doing, right? That's all it's doing. It does it very well. It's very creative. But when we have all of these technologies now, especially when we can create a medical professional from a chatbot, there is a huge amount of ethics necessary and licensing necessary for that, because people will take that as gospel. And it isn't until a person with legal responsibility tells you. And an AI agent just isn't that. So, one of the things I get asked all the time, and it kind of cuts across that, it's tangential, is, will AI replace me? No, it won't. But somebody who can drive AI better than you will. Because it makes them much more efficient. If I'm a GP, and I have my, not Google, but my chatbot, who's probably got 20 IQ points better than I have, right, across all of medicine, and I ask it a question, it's my legal responsibility to validate that. Chatbot can't do it for itself. What they have just done is removed all of that sense checking. It's a travesty. Yep.
Yeah, just going to ask how you sort of solve the issue of data storage, where we've seen like the memory chips in Teslas, for example, go bad, where you need to preserve that evidence forensically.
So,
do that in a pacemaker where you
Well, there's a number of strategies, and we do this already. So one is using error-correcting memory for a start. The other is that memory is now cheap, so you can have a gig. So this is just text data. This is sensor data that we can log. Even if you were doing it 3 or 4 times a second, that still is a huge amount of space for that kind of data to be represented. And then you can have a rollover. So you have a movable window of a month's worth of data, because as an engineer, if I'm sampling 4 times a second, I know how much data that will consume in a month. I provision that amount of memory, I give it error-correcting memory, but what I also have to do then is provide a feature or tool set that will allow data recovery or automated data extraction. So I can preserve the data unless I only need to go back a month, right? So in a car crash incident, I would only need to know what it was maybe processing 5 minutes before that, right? 2 minutes, 30 seconds, right? So that's the critical part. If you're in a plane, they go back only half an hour, actually an hour, maybe at most, right? Flight recorders don't actually record that much data, but they do it in a continuous loop. So these are the strategies that we could use for that. Plus, if error correcting memory goes bad, right, we could, it's within our gift to design that device so that we might be able to, I'm not suggesting we use SD cards, but there may be some very simple way of being able to swap out bad memory, depending upon the device. But remember, these devices have a lifetime. 10 years is a long time for an implanted device like this. So it's not as though they have to last forever. They just have to last for their design life, which is usually somewhere between 5 to 10 years.
Okay, any more questions? I'm going to cut off. I'm afraid you're welcome to find them later on. Can we give a round of applause for Adrian?
Thank you.